This lesson is about one of the two ways that Java provides to execute a separate thread. Any class that extends the thread class can be executed as a separate thread, and this class extends the thread class, and it starts two copies of itself running at the same time. The class has three private variables, so each instance of the class, each thread, has its own set of variables. Now this class has a main method, so it can be executed from the Java command line. The main method creates two instances of itself and calls the start method of each one. The start method is defined inside the thread class. It creates a new thread of execution and uses that thread to call the method named run. Then the original thread returns from the start method and continues. This can be done any number of times, causing any number of calls to the run method, each by a different thread of execution. Each of these two objects is created with its own name, counter value, and delay. The run method of a thread is sort of like the main method of a program. It's where the thread starts execution and the thread stays in execution until the run method returns. In this example, the run method never returns. It continues to execute until the program is interrupted. Inside the loop, the name and count value is printed, and the thread is put into sleep mode for the specified delay. The value passed to the sleep method is the number of milliseconds the thread is to pause. The two thread objects are given different names, different starter values, and different delay times. Here's how it runs. You can see that they're both running, with one of them on a 2-second pause and the other on a 5-second pause. They run at different speeds. The number one thread executes more often, so it has more entries in the list. Also, its counter gets ahead of number 2. Now, this example only has 2 threads, but you can actually make as many threads as you'd like. I tried more than 2, but the output was confusing and a bit hard to follow. Let me show you an example of a separate thread being used for a purpose. This is an example of an animated bouncing ball. This is a main window which contains a single component, a canvas object that contains the bouncing ball. A thread object is used to animate the bouncing ball. The canvas object is passed to the thread object's constructor, and then the animation is started. The animation thread class is quite simple. It has a run method, the same as any other thread, and in the timing loop, the repaint method of the canvas is called. This causes the update method of the canvas to execute, which moves the ball to its new position, and then a new image is painted. Here's what it looks like. This is the result. It works, but there is one drawback in doing it this way. The bouncing ball class has already extended the canvas class, so it could not extend the thread class to do its own animation. It somehow seems that it would have been a bit cleaner to have a self-contained animated component. I'll show you how to do that. In the next lesson, I will show you a way of doing the same animation without the requirement of an extra animation class. This lesson is about the second of the two ways that Java provides to execute a separate thread. Any class that implements the runnable interface can be executed as a separate thread. This class implements that runnable interface and starts 2 copies of itself running at the same time. The class has 3 private variables, and each thread uses a different instance of the runnable, so each thread has its own set of variables. Now this class has a main method, so it can be executed from the Java command line. The main method creates 2 instances of the class and then creates a thread based on each one. Once the thread is created, the start method can be called. This causes the new thread to call the method named run, which is the only method defined by the runnable interface. The run method of a runnable object is sort of like the main method of a program. It's where execution starts and the thread continues to exist until the run method returns. In this example, the run method never returns. It continues to execute until the program is interrupted. Inside the loop, the name and count values are printed. The thread is then put into a sleep mode for a certain number of milliseconds. Here's how it runs. You can see that they're both running. The output from this runnable demo is the same as it was for the thread demo of the previous lesson. The two are really the same program. The only difference is the technique used to start the threads. The two threads are running at different speeds. One uses a 2-second pause and the other uses a 5-second pause, so the number one thread executes more often. Implementing an interface instead of inheriting a class makes it possible to include both the component information and the thread information in the same class. Now, this program consists of a main window, and it displays one component, a self-contained animated component. All that is necessary is to add the component to the display, then call its start method to start the animation. This class creates the display and manages its own animation. For it to be a displayable component, it must extend a component, in this case, the canvas component. Now this runnable component has a start method. This is not the same start method as the one in thread. The method here is to start the component animation. A local boolean named running is checked to determine whether this component is already running. If it is running, nothing is done. If it's not running, running is set to true, and a new thread is constructed. The thread is based on this runnable object. Then the start method of the thread is called to kick off a new thread of execution. This new thread calls the run method of the runnable, which will stay in execution as long as running is true. Now this stop method can be called any time. All it does is clear the running boolean, which will cause the run method to return. And the run method returning will halt the animation and stop the thread. All that happens during the animation is the repaint method is called in a timing loop. This updates the display and paints a new frame. Here's what it looks like. This construction seems to be a bit cleaner. The animated component is self-contained. For another thing, this animation can be stopped and started any number of times. You could add methods for clear, reset, a color setting, anything you'd like. You can build any kind of animation based on this design, and you can use the same animated component in an applet. In the next lesson, we will look into synchronizing threads when they're sharing code. When you design a program to run as multiple threads, the threads often share data items. In fact, this is a very effective way for one thread to communicate with another. One thread can set a value and another thread can check it. But there's a problem. If two threads have the ability to modify the same variable, there is a synchronization problem. Let me show you. This is a class designed to run in threads and interfere with itself. These two static variables, a counter and a flag, are modified by both threads. Each thread is consistent in what it does, but with both of them modifying the values, they interfere with one another. In this loop, if the flag indicates that the value is 0, the counter is incremented and the flag is set to false. If the flag indicates that the counter is not 0, the counter is then decremented, so it should become 0, and the flag is set. The two threads can interfere and get the flag and the counter out of phase. Here's what happens. The numbers printed should be either 0 or 1 if there were no interference between the threads. But the testing of the flag, the changing of the flag, and the changing of the counter don't happen in the order they were programmed. The two threads interleave at random and the values drift. This can happen even inside a simple increment or decrement. Both threads could load the value, and one could increment it while the other decrements it, and the last one to store it back is the winner. But you can prevent that from happening. This is the same program, except the code that tests the flag and updates the counter has been moved into a method. All that happens in the body of the loop is a call to update. This is the update method. It is synchronized. That means that only one thread at a time can call this method. If a call is made to the method and another thread is already inside the method, the new caller must wait until the first caller is out before it can get in. As a result, the updating of the data field happens in the order the code is written. There is no longer interference. It runs like this. The two threads are now taking turns calling the method, and because it's synchronized, neither one will interfere with the other. You can see the result. The counter stayed at either 0 or 1 because the code was executed one thread at a time. This was an example of a synchronized method, and you can synchronize any method. You can even synchronize an entire class, which means every method in the class is synchronized. The next lesson is more about synchronization and how you can handle the locks that go with it. In the previous lesson, you saw how to synchronize methods, but you can synchronize more than just methods. You can synchronize blocks of code. But before I show you how that's done, I need to tell you about the monitor. The monitor handles locking required for synchronization. The Sun documentation calls it different names. Often you will see it referred to as just the monitor, but you will also see it called the intrinsic lock or the monitor lock. Same thing, different names. It is a lock that recognizes the thread of execution, and when it's in operation, it enforces exclusive access by a thread. Now, recursion is okay within a synchronized method. That is, the same thread can call a synchronized method as many times as it wishes. Only other threads are barred. Every object has a monitor associated with it. If you have more than one instance of a class, the lock in one of the instances has no effect on the other. When a piece of code is marked as synchronized, any thread wishing to execute that code must first acquire a lock from the monitor, and the monitor remembers which thread, if any, already has the lock, and only that thread is given access to the code. When a thread exits from the synchronized code, the lock is erased, and the lock stays erased until a thread hits the synchronized code again of the same object. This is the form of the synchronized code we saw in the previous lesson. The entire method is synchronized, so it will stay locked for any thread until the method returns. The return could be a return statement in the middle of the method, or it could be because of a thrown exception. Remember, the monitor associates with the object. Entering a synchronized method locks all the synchronized code for that object, so two synchronized methods can refer to the same data items from the same object and they will not interfere. But if you refer to the same data items from two objects, even if the methods are synchronized, they could interfere. But there is another approach. You can use an object to lock a block of code. You can do this with any object because every object has a monitor. If you declare the reference to the object as static, then you can lock it from multiple objects and you will always have exclusive access. Alright, that's pretty much it, but I've got a couple of caveats. An object can use its own monitor to lock a block of code. So it's not necessary to lock entire methods. You can limit your locks to blocks of code within methods. So it's possible to block several snippets of code within a method, which will allow multiple threads to execute the same method, but they will wait and take turns at sensitive sections. A synchronized static method does not associate with an object because a static method is associated with a class, not an object of the class, and monitors only exist for objects. But a static synchronized method does work. It uses the monitor that is associated with the object of the class definition. If you find that confusing, look up class in the Sun API documentation. The object in question is an object of the class. Anyway, it works. In the next lesson, we will look at how threads handle interrupts and joins. You have limited contact with a thread once you set it in motion. You can use global variables to set flags, and you can pass other information. But as we saw in some of the previous examples, a thread can spend a good bit of its time sleeping. You can issue an interrupt and wake it up if you need to. To show you how this is done, I'll use a variation on the bouncing ball thread example from previous lessons. In this one, the thread will receive an interrupt from the main program and change the color of the ball each time it does. The first change made to the program is the addition of a button on the display. The button causes the action performed method to be called, and the interrupt method of the thread object is called from that. This causes an interrupted exception to be issued to the thread. The call causes the sleep method to return by throwing an exception. Quite often this exception is set to cause the run method to return, thus killing the thread. But for this example, this exception will just cause a call to change color of the canvas to change the color of the bouncing ball. The color change is quite simple. All it does is increment the index into an array of color objects. This index is then used to select the color when a frame is painted. Here's how it runs. This is the animated window with the button. Clicking the button causes the next color in the array to be chosen. The color normally remains the same. It only changes when the button is clicked. It happens instantly because the interrupt causes an immediate call to the color change method. Another important way to communicate between threads is the concept of join. It happens in multi-threaded programming that you send a thread off to do a job, and you may reach the point where you don't want to go any further until the thread has finished. So you need to wait for it. For example, this sort of thing can happen if you've spawned a thread to get some information from a database or over an internet link. You can design the thread to store the data somewhere and then quit. Before you get the information that the thread was supposed to retrieve, you need to check whether or not it's finished. You can do that by calling the isAlive method, which returns true if the thread is still running and false if it is not. If it's still running, you can stop your thread and wait for it by calling the join method. This method will not return until the thread has finished. And there is another version of this method that will wait for a period of time instead of waiting forever. And there are other things you can do, such as changing the priority of a thread or checking whether a thread has been interrupted, or causing one thread to yield to another temporarily for execution. But you probably don't want to get too complicated with your thread controls until you know for sure you've got a problem. This stuff gets really hard to debug. In the next lesson, we'll take a look at deadlock and some other thread problems. You know what it's like to click on a button or something and get no response. You don't want your application to act like that. You want it to appear to be alive at all times, and that's what this lesson is about. Some things that can reduce or remove the liveness of your application. The first one is deadlock. It's the worst because it completely locks up the program, so the only way to get it going again is to kill and restart it. It comes about when two threads are trying to access the same resource and wind up waiting for each other forever. This is a class that's specifically designed to deadlock. This is a thread class, and when it runs, it creates two instances of itself and starts them both running. It contains two lock objects. They are static and public, which means they are global, so the two threads can share the same lock objects. This is the run method. The first thing a thread does is acquire a lock on object 1. Then it announces it is holding a lock on lock object 1 and going for 2. Then it tries to acquire the lock on object 2. Then it announces it has a lock on both. When it exits from the synchronized code, it announces that it has released both locks. Then it does the same thing again, but this time it tries to acquire the locks in opposite order. It first goes for number 2, then goes for number 1. These calls to yield are here to make sure that the threads take turns executing. It's just chance that the two happen to get into the right positions to deadlock, and this increases the chance. Here's how it runs. You can see from the output that the two are waiting to acquire locks. Apple is holding a lock on number 1 and going for a lock on number 2, while Orange is holding a lock on item number 2 and going after number 1. That's a deadlock. It's also called a deadly embrace. Neither thread will ever continue. The program has crashed. This is a very simple example. It usually happens in a much larger venue with hundreds or even thousands of lines of code involved. It's a major problem when locking portions of a database. For example, if you need to update a customer record to add an invoice number and update the invoice file to add the invoice, make sure you lock the two data files in the same order, or you can get a deadly embrace. Another problem is Livelock. It's not always as final as deadlock. The program can keep running, possibly. At the very least, things do get sluggish. It happens when an action by one thread causes an action on the part of another, and then that action taken by the second thread causes an action to be taken by the first, which again triggers an action. In effect, the two threads are so busy responding to one another that they don't have time to carry on with the fundamental task of the program, and that often means the user gets no response. Livelock, or even a simple loop, can be the cause of starvation. It happens when one thread is taking up all the time and another thread that has a job to do can't get the job done. We've all seen starvation in GUI applications. You click the mouse on a button and nothing happens. About the time you decide to kill the application, it starts to creep forward slowly. This is starvation. One thread takes a long time in a synchronized block of code and starves the other threads waiting for access. Be careful what you synchronize. In the next lesson, we're going to look into volatile data items and atomic operations. An atomic operation is one that completely finishes without the possibility of being interrupted. For example, the simple operation of assigning a value to an int is an atomic operation, but some operations may seem atomic, but they're not. For example, the simple act of incrementing an int may not be an atomic operation. Inside the compiler, the operation is converted to 3 steps. To perform the operation, the value has to be loaded into a register, the register incremented, and then the register is written back into memory. And the flow can be interrupted between any 2 of these operations. By the way, the reason this is part of the Java language is that it was an atomic operation on the machine for which C was originally written. It was possible to increment a location in memory. Some things are atomic, but you can depend on very little. If you read or write a reference variable, the operation is atomic. Using the new keyword to instantiate an object and store its address in a reference is not atomic. The object's address could be stored in the variable before the constructor has finished its work. If you simply read or write a variable value, it is atomic except for long and double. Those 2 may require multiple operations. But you can make any variable atomic for reading and writing by using the keyword volatile. This keyword is used to let the compiler know that a variable which can be accessed from multiple threads is subject to change at any time. In some cases, it is possible to use the volatile keyword instead of synchronizing the code, but do be careful. It's sort of a light version of synchronized. It's less coding, and it causes less overhead, but it does less. It's very easy to set up a volatile variable. Just use the volatile keyword when you declare it. After that, if your program uses the value of the variable more than once, this guarantees that it will always use the current value. Without declaring a variable as volatile, the compiler feels perfectly within its rights to use older and possibly out-of-date version of its contents. Also, the thread may not store a modified value back as soon as it otherwise would. In the next lesson, we will look at the things you need to do to create an immutable object. An immutable object is one that cannot be modified. The only way to get a modified version of an immutable object is to instantiate a new object with the differences. The overhead involved with creating a new object is not as great as you might think. Java is very efficient at constructing objects from classes, and there is a savings in the amount of code necessary to protect a mutable object. And the garbage collection is actually simplified. You are familiar with the string class and the advantages you have from it being an immutable class. You know that you can store a reference to a string somewhere, and it will be the same when you come back. There are a few specific things you need to watch out for when you write an immutable class. This is an example of an immutable class. It's not the best coding style possible, but it's shaped this way to show you the things you need to do for immutability. First, you make all fields final and private. They need to be private so they can't be modified externally. Making them final is really for your own protection, so you won't accidentally write code that writes to them. Being final, they can only be written to when an object is constructed, such as in the constructor. Any other time you try to write to it, you will get a compiler error. This means that you can't inadvertently write set methods to change the value of the variable. Also, you shouldn't allow subclasses of this class. The easiest way to do that is to declare the class as final, as I've done here. Another way to do it is to declare the constructor as private and write a static factory method to produce objects of the class. If you need to store internally the reference to a mutable object, don't let anything outside the class have access to it. In this example, It's passed an argument on the constructor, and a copy of it is made. That's because the original rectangle object could be modified externally later, and that would break immutability. Synchronizing the assignment code in the constructor is a matter of thread safety. This object could possibly be accessed from a second thread, and the access could occur in the middle of construction, causing an erroneous value to be returned from the get method. You can write get methods for all the values, but be careful. If your class contains a mutable object, then return only a copy of it in the get method. Of course, if your class contains an immutable object, such as a string, you can return that. In the next lesson, we'll start looking into how Java can talk over the Internet.